Hey guys, Logan here from the Web3 Foundation Technical Education team. Today I want to talk to you about the roles and responsibilities of validators. So as some of you might know, Polkadot has recently transitioned from its proof of authority phase, or its POA phase, to the proof of stake phase, or POS or NPOS for nominated proof of stake. So the major shift that happened during this transition was that the network went from being secured by a limited set of 6 authority nodes ran by the Web3 Foundation to now being secured by a decentralized, permissionless set of validators that have economic stake in the form of the DOT token backing them. So in this video, I just kind of want to go over what the role of the validator is in the Polkadot network. What are some responsibilities the validator has for maintaining the network, as well as some responsibilities the validators have to their nominators. And then at the end, I'll talk a bit about what you can do today to get started as a validator, maybe first on the Kusama network and later on the Polkadot network. So the first thing I want to cover here is one of the roles of the validator node. So one of the roles of the validator node is to participate in the consensus mechanisms of Polkadot. Now, Polkadot has what's called a hybrid consensus. This means that it has decoupled the acts of block production from the act of finalization. So there's numerous benefits to doing this, but the major benefit is that the slower finalization mechanism can operate kind of as a separate process to the block production mechanism, which means that blocks can be produced faster than they would be if they needed to attain finality on each block. So since you know that there's 2 separate consensus mechanisms, I'll start here with the finalization mechanism, the finality gadget known as Grandpa. So Grandpa's job for the validators is for them to communicate with each other and to perform what are called votes on different possible chain states, and whichever chain has 2/3 plus 1 votes from validators becomes what we say is finalized, which means that that chain can't be reverted at some point in the future. So you know that when you see your transaction enter into a block, and that block sometime later gets finalized by 2/3 plus 1 of the validators of Polkadot, you know that your transaction is in the chain for sure. So in this diagram here, what this shows is in the gray box we have the validator set, and to the left here we have the blockchain. So this gray box at the left is the first block, or the genesis block of the blockchain. Then we have block 1, block 2, block 3. And then we see in the 4th slot here, we have actually 2 competing blocks produced. So we have block 4A and block 4B. And then as this continues, we have block 5A, we have block 5B, and we also have block 5C get produced. Now this can totally happen because in the block production mechanism called BABE, validators will be essentially drawing a lottery ticket or a random number that decides when they get to produce a block. So if more than one validator happens to produce this random number that gives them the lottery ticket to produce a block in a particular slot, we can have the case that more than one block gets produced. So the question kind of comes to which one of these chains. We have kind of 3 different chain states here. We have the chain up on top, let's call this chain A. We have the chain in the middle, let's call this chain B, and then we have the chain at the bottom, let's say chain C. So which one of these chains will be is our chain, right? Is the chain we want to follow? Is the chain that the validators will finalize? So what the validators do is that they start to talk to each other to say what their view of the different chain states are, and then they vote on what they think the best chain state is. Now the rules are a little bit more complex than that. I just said the best chain state. In reality, there's a few different qualifications that the validators will take into account to determine what I call the best. But essentially, whenever the validators come to consensus by getting 2/3 plus one of all of them to agree on a particular best chain, that chain becomes finalized. So there might be disagreement though. There might be the case where different validators vote on different chains, and this is what we have in this diagram here. So we have this validator up here voting for chain A. We have 4 in the middle voting for chain B, but actually 2 of them vote for 5B here, and 2 of them vote for 6B. So they both vote for chain B, but they vote for different blocks in that chain. And then you have these 2 validators down here voting for chain C. Now, what will happen is that none of these light pink blocks will be finalized. But what will happen is that the common blocks that have 2/3 plus 1 votes will become finalized. Because we know that validators will vote consistently, and when they have voted 2/3 plus 1 on a particular chain history, to vote consistently in the future, they must continue to vote on that chain history. So if we look down here, we see all validators voted on a chain that contains at least these 4 blocks, these first 4 blocks here. So we know that those can be finalized. We also have all but 1 validators voting for chain histories that contain this 5th block in the B chain as well. So what will happen is that because this block also has 2/3 plus 1 votes, it'll become finalized as well as the 4 blocks behind it. So this is what we call the canonical chain. So one of the validator's roles is to determine the canonical chain. Okay, so that covers the grandpa finality gadget. But now let's talk about the other side of Polkadot's hybrid consensus, Babe, the block production mechanism. So I mentioned it before, but the way that Babe works is that there's a primary block production and a secondary block production. So Polkadot is kind of laid out on a timeline. And this timeline is divided into what are called eras. And each era is itself subdivided into a number of slots. So at each one of these slots inside of an era, validators will do the primary mechanism, which is they will draw a random number. So all validators draw this random number, and if the random number falls below a certain threshold, the validator who pulled that random number will produce the next block. Now, if there's no validator that produces a suitable random number that falls below the threshold, it'll fall back to the secondary block production, which is just a round robin of validators that are assigned to the secondary slot. So if no validators see that anyone else has produced a primary block in a certain slot, then it'll just fall back to that person, that validator who was assigned in the secondary mechanism. So that should explain what the numbers in this diagram 1 and 2 mean. So we have here a blockchain, again, that is being progressed by Babe, and blocks are being produced both in the primary mechanism, which is represented with a 1, and the secondary mechanism represented as a 2. So as we can see, forks are created when blocks are produced in the same slot. So the first fork occurs here in slot 3 because 2 primary blocks, 2 validators pooled random numbers that fell below the threshold were produced. And then we see up on the top fork a bunch of secondary blocks get produced, and finally a primary block at the end. And then we have different configurations here. So what this kind of demonstrates are the different scenarios and what actually qualifies blocks as being best blocks when they're being considered for finalization and canonicalization. So the second role that validators perform in the Polkadot network is this BABE block production mechanism. A third role of validators is to secure the parachains and to validate the parachain state transitions. So in this role, validators actually do a couple things. What they do is that they will be subdivided into subgroups, and the subgroups will be assigned to particular parachains. You can see this image, we have a subgroup being assigned to a purple parachain and a subgroup being assigned to a blue parachain. And then they will receive state transitions from the parachain's collators, these little dots in here, and they will check these state transitions against the state transition function that's stored in the relay chain. So they're kind of the gatekeeper of how parachains can progress, how they can transition themselves. Now, as part of this role, they're also dividing up data among each other in what's called erasure-coded pieces. So what basically happens is instead of keeping all of the parachain data locally in their own kind of environment, they divide this data into smaller pieces that can later be reconstructed with only a subset of the entire pieces. So the property of erasure codes that validators benefit from is that you can create a code of, let's say, 5 pieces, and divide this out among 5 validators, and then you only need 3 of these 5 pieces to recover the full data from before. So you have each validator holding a smaller piece of data, and you also have the ability to later ask the validators for that data and to reconstruct the parachain state if they need to. So this is part of the reason why parachains, why validators can be shuffled among parachains without having to download the entire parachain data for each parachain that they're shuffled among. Okay, so now you know about the roles of the validator. I'll talk about what the responsibilities of a validator are and what are the requirements for running a validator. So here we're on the Polkadot wiki. We're on the validator guide for the Polkadot network here. So if you're interested in running a validator on Kusama, we also have a Kusama guide. And the two processes are very similar, but they do have some key differences. So what I want to talk about first is the hardware requirements for validators, because that's kind of one of the key differences between the Kusama and the Polkadot network. So in the Kusama network, the hardware requirements are kind of loose because that network is kind of built on this idea and culture of moving fast and breaking things and kind of testing the limit of what you can do. On the other hand, Polkadot is kind of a more conservative approach. It's more tested. It's tested on Kusama first, and it's more. It holds more value, and for this reason, we want stronger guarantees on Polkadot than what we get from the move fast, break thing attitude of Kusama. So for this reason, there's a kind of a stricter set of hardware that's recommended for validators to run. This is what's called the standard hardware. And the reason it's a standard hardware is because this is what the benchmarks for the Polkadot code base were performed on, and how the the weights of the transactions. So what end up influencing the cost of the transaction and how much space these transactions take to process, how much time they take to process, and how much space they ultimately take up in the block state. So it's recommended that validators run the standard hardware. There's not really anyone that's going to sit over your shoulder and call you out if you're not, but it's overall a benefit for you as a validator because you'll be running the code at the speed that the weights were designed to be ran at. So you'll end up not being slower than other validators, and therefore you shouldn't be at any kind of disadvantage if you're running this hardware. So I'll just go over a bit about what this hardware is. So it's recommended to have at least an Intel i7 at 4.2 gigahertz. To use a NVMe solid state drive, should be reasonably sized to handle the chain growth. So since we're in the very early days of the network still, it's probably okay to kind of keep this on the low end for now, but just be aware that if you do, say, just start out with 30 gigabytes or 50 gigabytes or 80 gigabytes, you might have to look back in about 6 months and increase that possibly every 6 months thereafter, right? So if you want to kind of just put a bunch of storage on your validator and forget about it for a little while, you'd probably want to put at least 100 gigs or 200 gigs, and then you'll be set for the next little while that we can foresee. Now the memory was benchmarked on 64 gigs of memory. So this is something that could possibly be cut down with very little performance loss. But again, to be on the safe side, it's recommended to have this 64 gigs of memory. So where you actually run this hardware is totally up to you as a validator. So if you want to run it in the cloud, that's a possibility. Just be aware of the different trade-offs you have, namely that the infrastructure ultimately falls in the hands and responsibility of this cloud provider. Also, that if something happens to this cloud provider and multiple validators are running on that provider's infrastructure, multiple validators could get taken down at once, which would increase the severity of the slashing that would happen. That's because Polkadot uses what's called correlated slashing. So the more validators that are found to have committed a misbehavior within a single era, the more severe the slashing they will get at the end is. So you can also run then on your own hardware. So it's recommended that if you do this, you know what you're doing, because you don't want to set up a validator at home and then have your consumer grade internet shut off for some reason, or just how flaky home internet can be. So kind of the optimal solution would be to host your validator on very reliable infrastructure, but not on the same infrastructure that anyone else is hosting their validator. So if you can find something like a small server farm somewhere that you can visit yourself and kind of look around and make sure it's reliable, that would kind of be the best place to put a validator. But there's always trade-offs between kind of the whole spectrum of running a validator at home to running on the cloud and then the private data centers and so on. So validators will need to bond dots. So they'll need to have some kind of skin in the game, some kind of economic stake to actually become a validator. Now there's no minimum amount a validator needs to bond to signal its intention to validate. It can be as small as 0.01 dot tokens. But the self-stake, as it's called, is something that nominators might pay attention to when they're choosing to nominate your validator. So it's a way for a validator to kind of show how much of their own skin is actually staked on their operation. So they'll need some kind of bond. It's a requirement, but that bond is kind of up to the validator how much they do. So this is probably a good time to also mention the responsibility that validators will have to their nominators. Namely, the responsibility is that they will operate a good service with little downtime, and that their validator won't be stuck in a situation where it will eventually get slashed. Because if the validator gets slashed, all of the nominators that are nominating that validator get slashed as well. So to illustrate that, I just will bring up this example of a validator on the Polkadot network. And we'll see here the nominators that are currently backing that validator. So because of the way that the election algorithm works, Fragment, nominators that nominate a specific, particular validator aren't guaranteed to actually back that validator, because the election algorithm will kind of shift around the nominations and try to ensure that each validator has as equal backing as possible. So there's gonna be definitely variations between the most backed validator and the least backed validator, but Fragment election algorithm will try to minimize that difference as much as possible. So while the nominators are nominating a particular validator, the tokens that they have in nomination, their dots, will be at risk, just the same as the validator's economic stake is at risk. Finally, I just want to talk about the community presence of validators, because this is something that I think really does come down to something that can distinguish between different validators in the ecosystem. So what I mean by the community presence is just kind of that validator's presence on the internet. So whether they're active in maybe the Riot chats, whether they have their own website homepage set up where you can go get information about their setup, or if they have a Telegram room, and so on. So these are all kind of added benefits to kind of a validator's own community that can make it more attractive and draw in more nominators to them. So it's not something that's required at all for running a validator. If you want to, you can run a validator and be totally anonymous, or you can run a validator under a pseudonym, or you can run a validator as a kind of service provider or a business in its own right. So we see some people actually doing this in the Polkadot network, because validators are getting paid out rewards when they perform their roles correctly, and along with the protocol. The validator is actually it's making some returns for its effort. So it's not an altruistic effort. So if you're looking to set up a validator, one thing you might want to look into is different ways that you can distinguish yourself to the nominators, because as the network progresses, the number of nominators will increase, but also the competition for the nominations will likely increase as well. So this is kind of a challenge to any prospective validators out there, to kind of come up with the next best thing for being a validator, for having a validator community or being a validator. If we just scroll down this list, we can see. Sorry, I wanted to close this. We can see just some of the identities that the validators have set. So in Polkadot, there's a identity palette, and this contains kind of just simple logic for setting an on-chain identity and putting your name on an address, basically. So we can see just some of the names of validators. If we click on one, we can get some more identity information that they have shared on chain. So we can get their email, their website, and their different handles on different social networks. This is just one way that if a nominator, for instance, is looking down this list, they're probably a lot more likely to choose a name that is recognizable to them or sounds cool to them, versus just kind of a long string of characters that they might not even have any. They might not have any idea who is behind that validator. So another thing I want to mention is that running a validator is a security-sensitive operation. Because there's going to be competition among nominators, there might be incentive for eventually competitors to find ways to take down their competitor validators. Or a malicious actor just wants to take down validators to watch the world burn and for validators to just lose out on their rewards. So if you run a validator, what you want to do is you want to make sure that that validator isn't exposed to the internet in a way that it can be taken down by what's known as a DOS attack, or a denial of service attack. And the most common way to do this is to use a firewall with sentry nodes. So sentry nodes are kind of an outer layer of nodes that exist on a private network with a validator, and are the only waypoints between that validator and the rest of the peer-to-peer network. So any gossip that goes to a validator has to go through one of the sentries first, and the validator is only connected to these sentries. You also want to look into getting monitoring tools for your validator. So you want to have a way to follow the logs, maybe get some alerts on your cell phone through text messages or on Telegram when different things happen in the network, when different things might happen for your validator or your infrastructure. So you need to kind of set up a suite of tools around your validator as well to make sure that it's a secure process. All right, so the final thing I want to talk about is the steps you can take to become a validator on first the Kusama network and eventually the Polkadot network. So Web3 Foundation runs a joint program with Parity Technologies called the 1000 Validators Program. And here's the webpage. It's available at 1000-validators.kusama.network. The purpose of this program is to onboard new validators onto Kusama and give them the experience of running a validator and running this infrastructure and all of the suite of tools that are involved and building their community and so on, and to eventually transition to running their own self-sufficient validator on Kusama and possibly Polkadot as well. So in the program, Web3 Foundation and Parity nominate validators on a rotating basis so that you can join in, and the only economic stake that's required from you as a member of this program is 50 KSM, just to kind of demonstrate that you have some incentive also to operate a good node, a good validator node. So if you're interested in running a validator, I think this is probably one of the best ways to get onboarded into doing it. You can visit the website and click the apply button here, and it'll take you to a nice form that you can fill out, and we'll later get a response for that. If you're not already in the Riot channels as well, I urge you to join the Riot channels and ask any kind of questions that you might have there. So, thanks a lot for joining me, guys. I hope you learned something about the roles and responsibilities of running a validator. If you have any questions, feel free to either send me an email at Logan@Web3 Foundation. Join the Riot rooms. So at the bottom here, you should have some links to join the Riot chat. That's a great place to ask questions if you ever have any. You can find me there as well. And I hope to see you in the community. See you next time.